For all those who appreciate the work that we're doing here on Standing for Truth, please hit that subscribe button because we are just getting started.
All right, it looks like we are live for another video that is sure to be one to remember, guys. We have so much content for you guys to look forward to as well. I want to point out the fact that we've got a lot of great interviews, further rebuttal videos. We're just getting started on these rebuttal videos, guys, and debates set for the future. Lots of content coming your way. Today, though, we are now starting our series debunking Erica, who goes by Gutsick Gibbon on YouTube. We're going to be debunking her claims now on geology and age of the earth from her master dodgeball video rebuttal to us. That was 3.5 hours long. Today, we focus on oil exploration. This is going to be a lot of fun. Okay, guys. Now, I want to point out too, another brief announcement just to update you guys on everything that we have going on. We also have Team Dodgeball dodging Salvador Cordova. If you haven't seen his lectures, please do so, specifically evolutionary fitness and protein probabilities. Now, we have them dodging his lecture series really, really hard. For example, Dapper Dino, he has devolved into Diaper Dino, as Team Dodgeball has scoffed at Sal's lecture on evolutionary fitness, and yet so far we've got no takers to debate him on that specific topic. Now, here's the challenge to any evolutionist. Either the debate occurs on my channel or Sal's channel, or they can do a video response, and of course we will respond with our own video in return, as we always do. And if they accept the debate challenge on either my channel or Sal's channel, they can bring any moderator they want. Heck, they can bring 2 or 3 atheist moderators with them if they think that that's what's going to be fair. Now, before I hand it off to our good people here, I'm going to screen share for everybody just to let you guys know that so far we have absolutely decimated every single word spoken by Gutsick Gibbon in terms of her genetics-related arguments. So as I'm screen sharing here, guys, definitely check out this playlist, series refuting Gutsick Gibbon's latest attempt to refute creation. Absolute proof that none of our questions were answered, none of our arguments were even really attempted to debunk or answer, and we've answered all her questions. So definitely check this out, guys. And today's video will also be added to this playlist. And we've got a lot more coming your way on the age of the earth and geology related topics, guys. So enough from me. Good to see everybody in the chat. Like I said, this is going to be a lot of fun. We've already got a lively chat and we've got a lot of people here. So looking forward to this. I'm going to hand it over to our guests today. We've got Brother George, Brother Steph, and Brother Ramat. Guys, thank you so much for being here. You guys are muted, so just make sure that you unmute yourself before we get this going.
Ready to rock.
Ready.
Awesome. I'm excited. Brother George, did you want to take the lead on this one?
Well, yeah, just a brief introduction. Good morning, good afternoon, good evening, wherever you are. But just something that I noticed about that video of Erica's, either she doesn't have people around her that are advising her correctly, or she knows absolutely nothing about oil exploration or geology, to be honest. So if Matt just wants to play that short introduction of her video where she talks about oil exploration and the dating of rocks, we can begin the show.
Awesome. Oh, I'm sorry, Matt. Go ahead.
No, I was going to say, all right, just make sure everyone can see it good. I'm going to share my screen.
You're good to go.
All right, thanks. Let me turn it up. And let me know if you guys can hear it good or can't. I'll make sure it's loud.
As long as you clicked audio when you screen share, we should be good, brother.
I did not do that, actually.
Hey, listen, it's a good thing we caught it beforehand. And I will make it the full screen layout as well when you when you start the video. So good to see everybody in the chat. Nicholas, good to have you here. Sister Joe, Luca, Doki Doki, Honesty Angel. We got some good people here, guys. This is going to be one to remember. Make sure you share this
and
around,
hit the
guys.
like button.
And hit the like button. That's right.
I actually didn't see the button to share audio, so maybe it'll be fine.
Okay.
All right, let's find out.
Rate is, to our knowledge, constant. This is something that was admitted by the very creationists who were trying to prove that it wasn't. Decay also has a known final condition, that being all daughter material, and the process is indeed irreversible. Radiometric dating is also corroborated by a dozen or so independent methods as well, and the fossil fuel industry relies on its accuracy for finding said fossil fuels to the tune of around $250 billion annually. So this seems pretty solid.
Well, what shall we say about that? I must say I was a bit in shock when I heard Ulrika saying that, because it's totally untrue. It's absolutely not true that the history of geological layers play a part in exploration for fossil fuels. We find oil in underground traps, and I must say we showed it a couple of weeks ago in the video about salt domes. And what geologists are actually looking for are underground oil traps. They do this by identifying particular areas of the Earth's surface for specific shellfish fossils known as foraminifera, and they search especially for evidence for hydrocarbons. And then when these clues are found, they begin exploratory drilling. So I don't see a point, no.
No, I don't see her point either. And her claim here that supposedly fossil fuel exploration relies on dating methods for an industry that spends $250 billion annually. Oil is found in sedimentary rocks, Erica. She claims to be thorough, and I think we're going to show her today just how thorough she's really being on how oil exploration is, what it's really dependent on, and if it has anything to do with deep time and uniformitarian processes. So
we are looking for faults and structural geology and stratigraphy, and we identify these by seismic reflections, and
yeah, they've been using that for the past 70 years too, Steph.
Yes, they have used it.
Can you pause it there, please, Matt?
Yep.
I spoke to David McQueen for probably about an hour yesterday. Just for some people that may not know who David is, but he was involved in what's known as economic geology, that is exploring for oil, gas, gold, silver, etc. Mr. McQueen recommended a book by Dr. Tim Cleary titled Carved in Stone for geological evidence of the worldwide flood. So if anyone's interested, yeah, search for Tim Cleary, and the book title is Carved in Stone. Now, Mr. McQueen is the Assistant Professor of Geology at the ICR Graduate School. He earned his master's degree in geology and from the University of Michigan, while a National Science Foundation graduate fellow. He also has a BA in geology and an MS in geology. He also taught at university level at Virginia State University in petroleum geology, having studied it for 40 years. So he's quite well known in the industry. That particular quote there effectively talks about what they really look for, and they look for rapid sedimentation and evidence of porphyrins. Porphyrins are products of crude oil, and they're usually the result of plant material and, believe it or not, blood, hemoglobin. One of the things about porphyrins is they need, or crude oil, it needs to be buried quickly and deeply under pressure, because oxygen really destroys the whole process. So, yeah, Matt, if you can forward to the next quote, I believe, I think it's from Tissot and Walt. They talk here about petroleum porphyrins. As you can see, they have been identified in sufficient number of sediments and crude oils to establish a wide distribution of these geotechnical fossils. So this is one of the things that they actually look for as evidence of where they may undertake drilling for oil to determine further if they can gain further information, and therefore go into the more expensive process of drilling. Now, David tells me that he's examined drill cores from across the world, and what I found surprising when he mentioned this was, he says all the fossils from 100 feet down to thousands of feet, he says they don't find any evidence of transitional fossils, even from the deepest cores to the shallowest cores. That is an amazing feat, by the way. I mean, you'd think with all the cores that have been done across the world, they would identify some kind of transitional fossil in all those cores. Again, I'd like to say, I'm sorry, Erica, but you can't reliably and accurately date sedimentary rocks. Contamination through leakage makes it completely unreliable. You just can't date reliably and accurately sedimentary rocks. So dating of rocks has nothing to do with oil exploration. Okay, go to the next part, please.
Yeah, because the oil is found in this sedimentary rock. So.
Yes, correct.
Yeah.
And it's interesting to note that you need quick burial through sedimentation, just as you'd expect in a global flood, to ensure the required oxygen-free environment. It requires a deposition of a cap layer like the impervious shale we find in all the oil traps to seal the oil and gas from escaping to the surface. To reiterate, porphyrins break down rapidly in presence of oxygen and other oxidizing conditions. So it's important that the process be done quickly, and it has to be capped. Otherwise, everything leaks to the surface and you don't have all these oil wells sitting around underneath us. Yeah, one of the articles that David McQueen has written, you'll see there on the screen. It's from you can find it on ICR. It's titled "The Chemistry of Oil" by David McQueen himself. There's a link to that article in the description. I hope we've got that in the description, but if not, you can easily search for it. Just type in "The Chemistry of Oil" explained by Flood Geology, and it's I think probably a 5 to 6 minute read. Okay, thank you. Just move on to the next one. Yes, Erica. Just one thing here, Matt. Just pause it there. I'd like to acknowledge to the next part, please. I'd like to acknowledge the excellent educational videos that are available on YouTube on oil exploration. Please note that the videos you're about to see are not creationist videos. These are videos made by oil exploration companies themselves. Okay, the particular ones that we've got today are from Earth Science in Western Australia, Polar Petroleum, and Rutgers OEDG. So if we can play the first video, Matt, I think people will get the idea where we're coming from.
Kerogen. Under heat and pressure, kerogen gradually changes into oil or gas. The whole process usually takes at least 1 million years. At the molecular level, oil and gas are hydrocarbons made up of hydrogen and carbon atoms. The constant pressure and movement of the Earth's crust squeezes oil and gas through the pores or spaces within rocks. Some oil and gas reaches the Earth's surface and seeps out naturally into land or water. Often it is trapped beneath the surface by impermeable layers or rock structures, like faults and folds. Within the crust, oil or gas deposits build up and form reservoirs. Reservoirs are like vast sponges filled with oil and gas. They can be as large as a city. To find oil and gas deposits, geologists use a number of different survey techniques, including seismic surveys, gravitational surveys, and geological mapping. Seismic surveys use reflected sound waves to produce a 3D view of the Earth's interior. New technologies, such as four-dimensional projections and sophisticated graphic renderings of rock structures, are improving the way we find conventional oil and gas deposits. Energy resources that are currently difficult or expensive to extract are called unconventional oil and gas.
Yeah, thanks, Matt. If you could just pause it there. That first video was an introduction to oil and gas from, as I said, from the Earth Science, Western Australia. Now, they mentioned some uniformitarian assumptions there that it takes at least 1 million years for the oil to be created. We will show you later on from actual experiments that have been done in laboratories that it doesn't take anywhere near that amount of time to create oil. We'll also show you the paper that details these facts later in the presentation. So, Matt, if you could go to the next video titled Using 3D Seismic for Oil and Gas Exploration. It's a short video of around just short of 4 minutes. This will set the scene for a more detailed video of what geologists are actually looking for when they're actually drilling. Notice they don't mention dating of rock layers once in any of these videos. Not once do they mention the dating of the rocks as a criteria to find the oil. Thank you.
Planet Earth. If you look closer, you'll see that a whole other world exists beneath the surface of land and sea. Layer after layer of rock structures go deep into the Earth's crust, mile after mile. And trapped within these structures, along with other liquids and solids, you'll often find deposits of oil and natural gas, the world's two most important sources of energy. These famous fuels are in constant demand because they make the world go round, day in and day out. So how do you find something that's completely hidden beneath the Earth's surface? It's a mystery that people in the oil and gas industry are always trying to solve, and for very good reason. Drilling for hydrocarbons is expensive. And before they spend money on equipment and crews, exploration and production companies need a reliable strategy for pinpointing where to drill. Geoscientists have a secret weapon called seismic exploration, and it involves sending acoustic energy, which takes the form of wavelets, into the ground to get a sound picture beneath the surface. It's complicated, so let's start with the analogy of bats. Bats can't see very well, so they send out little waves of sound that bounce off of objects and then go back to their ears. It's called sonar. It gives them what you might call a sound picture of their world. That's a good example of how nature already uses a form of seismic acoustic imaging to locate objects. Doctors also use it for ultrasound imaging. Geoscientists use man-made tools to make the sound wavelets, listen to them, and then record them. When you want to know if oil and gas deposits are in a particular area, geophysical companies bring large trucks that have big vibrators on them. Most of the time, this is what generates the acoustic energy or vibration. They use geophones or very sensitive seismic microphones to hear the reflected sounds, but sometimes they set off small buried charges. They set many geophones on the ground in a line, and they are attached to a recorder inside another truck. The vibrators send thousands of wavelets down into all the different layers of the Earth. Some of the wavelets bounce off of the boundaries between the rocks below the surface and are reflected back to the geophones that are waiting to record them. Each geophone along the cable sends the received wavelets to the recording truck where they're recorded and stored. Here's what seismic looks like after it's been recorded. Basically, it's a bunch of squiggles. There are still a few more steps to go before it begins to look like an actual picture of the Earth's interior. Right now, the data is still in its raw form. To get a picture that actually looks like the Earth beneath us, the data has to be processed. It takes a large supercomputing PC cluster to process the seismic data. These computers go through all the different traces made by the wavelets and filter out everything we don't need, such as vibrations made by a tractor in a field nearby. Using really amazing computer applications and working on state-of-the-art workstations, geoscientists can see the seismic data translated into a 3D picture. You might be thinking, I don't see any oil and gas there. But believe it or not, geoscientists can look at this processed data with their trained eyes and make an informed decision about whether or not oil and gas deposits are in the geologic structures. Seismic data leads to a high percentage of drilling success with less risk to the environment. And in a world where the demand for oil and gas is increasing faster than the supply, good seismic information will lead to more affordable energy.
Thanks, Matt. Just pause it there. Please note again, they did not mention dating of rock layers once.
Right.
I noticed Luca's in the chat and he mentioned the impermeable layer.
That's right.
Luca, be patient. We will cover that. and it's nice to see Ogre in the chat as well, because from what he tells us, he's a geophysicist, so he should be able to really collaborate these points that we're making. The next part of the video, we really put everything together. It really tells you these are the three things that the geologists or geophysicists look for. They look for density, porosity, and permeability, and seismic reflection. And the next video, I think, will make that plain and clear. It's a reasonably, I wouldn't say long video, but I think it's around 10 minutes or so. And it sort of puts everything together into context, and you'll find a bit more about it as we play the video. This video, by the way, is from Rutgers, OEDG. That acronym stands for Opportunities for Enhancing Diversity in the Geosciences Program. Please, again, I'll state, these are not creationist organizations, okay? As far as I know, these organizations are secular and they're in the industry, so it's got nothing to do with creation. Okay, Matt, if you could play the video, and please, I'd like to acknowledge the videos, and please note that they're, in terms of fair use, they're really here just for educational purposes. So yeah, so play the next section, Matt. You'll notice they talk about the density and order.
Density, basically, you know how heavy things are. Okay, it's how much mass per unit volume you have. That's density. And obviously, everybody knows about how dense metal is or how dense a rock is, but fluids and gas also have densities. And based on that density, they're drawn more towards the Earth by gravity. So gravity acts on that mass to pull it down towards the center of the Earth. And if we take a look at a bottle where we put in some water, some oil, and some gas, you'll notice that they always come in the same order. The water goes on the bottom, the oil goes in the middle, and the gas goes on top. And that's the order they will always occur. No matter what I do with this bottle, the order always remains the same. And the reason is that water is denser, Oil is in the middle, and gas is the lightest of the three. And that's why they will always remain in that order. Now, if you think about what's in the ground, obviously the most abundant of these is going to be water. Water is everywhere. Okay, you dig a hole in your backyard, you'll hit water. Whereas oil and gas are a little bit harder to find. And those are the things that are going to be worth the most money. Now, the one thing I want you to notice when we look at something like this is that the oil and gas are always at the top. Okay, they always go to the top. So later on, you're going to learn how to drill for oil. And the one thing you got to keep in mind is that they always go to the top.
Thanks, Matt. Just stop it there. You'll notice that in the first part, they talked about density. That is the order of the gas, the oil, and the water. Not once did he mention the dating of rocks, Erica. Not once has he mentioned dating of rocks. In the next part of the video, they'll cover porosity and permeability.
Can I say something, George? Yep. He said something very interesting. There's water everywhere. No matter where you drill, you will find water. And that's another thing that they always say, that there is not enough water on Earth for the flood. But you hear this man saying water is everywhere. And that's exactly what the oil business shows us. There is more than enough water in the Earth.
Yes. How many times have we heard, where did the water go? It's right here, right below you.
Exactly. Yeah.
Yeah.
So I just want to underline
Matt, the next part.
Now, the next thing we're going to look at is something called porosity and permeability. Well, porosity is basically open space in any material. And any material you can look at has some open space inside of it. Some have more and some have less. So, for example, if you look at a sponge, there's a lot of air space in the sponge. That airspace is the porosity. That airspace can have water in it as well, but that's the porosity. It's not the sponge itself. It's an open hole.
George, can you pause it real quick, brother? I wanted to point out, too, just as good anecdotal evidence, because we've pointed this out in the past, but it doesn't stop these critics from repeating the same arguments, right? Because when they only have 3 or 4, and then we address them and debunk them, they have no choice but to repeat them. But Brother John Maddox from Logical, Plausible, Probable, he points out that he's talked to professionals with over 30 years of oil and gas exploration experience, and he's personally asked these expert-rated geophysicists who currently work to find oil. And when he asked them that question, they looked at him like he was being silly. And they asked, who's the ones that are claiming this? So this just seems to be like a minority view, an argument employed from those that hate flood geology and simply just want to fight against the young Earth creationist model. So forgive me, I just wanted to point that out.
No, I'd like to add something too. I've actually spoken to people that have been in the industry as well. I even spoke to a geophysicist who confirmed everything that I've actually researched. So it's not just the opinion of a retired civil engineer. Okay, so it's collaborated by people in the industry. Thank you. You can continue the video.
Yeah, go ahead.
It's not the sponge itself. It's an open hole. Swiss cheese has porosity. It's got those holes in it. So that's the porosity part. Now, if you take that sponge and you squeeze it, all the water is going to come back out of the sponge. And that is the permeability, the ability to flow from one pore space to the next. That's the permeability. So if you have ever seen bubble wrap, for example, bubble wrap, those were all little bubbles of plastic encasing air, okay? Now, that means it's got porosity because all that airspace is porosity. But can the air flow from one bubble to the next? No, not unless you pop it. Once you pop it, then it has some permeability. But until you do, it just has porosity and doesn't have permeability. Now, what we're looking for in rocks is to have both porosity and permeability or neither. Okay, rocks can have as I said, porosity and permeability. And here we have two different rock types, okay? The first rock, the one on the right-hand side, is called sandstone, this tan one. Over here on the left-hand side is shale. The sandstone is kind of basically made up of sand grains that are stuck together. The shale is made out of clays that have all been sedimented down and hardened. Okay, so what we can do is we can decide which one of these has porosity and permeability. So if I take a little bit of water and I put it on the shale, the water just runs right off the shale. Okay, and therefore it has no porosity or permeability. Now, if we take that, do that same test, and we put it on the sandstone, what we'll notice that'll happen is it will run a little bit, but all the water soaks up into the sandstone. Okay, so therefore sandstone has high porosity and permeability, whereas shale has no porosity and permeability. Now, if we were going to take the oil and the gas and the water that we just looked at, and we were going to put them into one of these rocks, which rock would you pick? That's right, you would pick the sandstone. The sandstone can store oil, water, or gas inside of it. And therefore, it is what is called a reservoir rock. The word reservoir means to store. So we store those things in here. Okay, and so that is where we would put all of our oil and gas if we were going to accumulate. However, if we go back and look at this bottle that we just had, we will notice that the gas is held up at the top. Now, so what would happen if we pulled the cap off of this bottle? Well, that's right. All the gas would escape into the atmosphere and wind up in the room rather than inside of this bottle. So therefore, the cap is what's holding it in. Okay. Now, the same thing happens with oil and gas accumulations. So we may be able to put all the oil and gas inside of this reservoir rock, the sandstone, but if we don't seal it in, it's going to all escape. So what we need is a cap rock, the shale. So the shale acts like a piece of saran wrap.
Thanks, Matt. Steph, feel free to jump in whenever you like, but as he mentioned, porosity and permeability of the sandstone and the opposite properties of the shale are important characteristics in where they actually find these oils. You should note, though, that the shale is the cap rock that prevents the gas and oil from escaping. And we usually find these fossil fuels at approximately 2 kilometers underground. That's 2,000 meters. I'm sorry, I can't give you what it is in miles, but I guess America needs to catch up with the rest of the world in terms of metric measurements. A bit of a dig there. Also, you should note the shape of the cap rock in the following illustrations. You'll also note that they mentioned that the oil takes 1 million years to form. We will show you later on that that's just not necessarily true. With actual experiments that have been done by, I believe one of the organisations is the Australian CSIRO. What's next? Yeah, the organic material had to be buried quickly and deep, preventing oxidation, and the shale cap layer needs to seal it from escaping. In millions of years, you would expect a gradation of sediments, but we find homogeneous layering, as we find in stratification experiments in flues. You'll note in these presentations, you get layering of sandstone, different materials than shales. I mean, if these things took millions of years, you would expect some kind of gradation of a mixture of materials, but you don't find that, which is just another evidence of quickly forming sedimentary layers like you would find in a global flood. So, Matt, if we can play the next timestamp, this one talks about the seismic reflection, which is really putting things together and then they identify the location, quantity of oils that are present before they actually begin to drill. So
actually, before you go, Brother
Yep.
George, I was just going to point out before, so the chat's very lively, and we're getting some great super stickers. Thank you so much, Doki Doki Bible Club. Doki said for $5, there's bubbles coming up today at La Brea tar pits. How long should this happen? Any thoughts, gentlemen?
Well, correct. Sorry.
It would continue until the oil and the gas is gone. So this is a good example of the point that George just made, that if you store the oil and the gas that long underneath a cap, then it will be leaked out by now. It would have been leaked out by now. Yeah.
Just some mathematics for people. It's quite noticeable that they mention that oil is usually found at around 2,000 meters. Now that equates to around 4,000 tons, metric tons per square meter. That's a lot of pressure. And what Steph just mentioned, you would expect all of that oil and gas to have leaked out if it was millions and millions of years as they claim.
Yes.
So yeah. And you'll note in the next part, they've been using seismic reflection for around 70 years. Now he mentions 6 decades, but please note this video is actually made in, I think, 2010, 2012. So effectively, they've been using seismic reflection for the last 70 years. Okay, so if you can play the next video, I'll just reiterate again for Erica. You can't reliably and accurately date sedimentary rocks, Erica, and they don't use the rock dates to find the oil. Please continue.
Now, in order to drill wells, and there's been a lot of things on television where you can see people drilling for well, coming up with oil. For example, if you've ever watched the Beverly Hillbillies, they made a movie out of it. It used to be an old TV show. The guy goes in the backyard shooting at a rabbit, misses the rabbit, and all this oil comes squirting out of the ground. Okay, well, that's not quite the way it works anymore. And you could get some oil and gas coming to the ground. The La Brea tar pits are actually oil seeping to the surface. But in general, the shallowest you need to drill a well is about a mile down to get oil or gas, a mile. And so I don't think you could find too many shotguns that can reach a mile down into the earth. So you have to drill. And drilling's not an easy thing. It takes a lot of engineering. It takes a lot of time. You're drilling through rock. It'll cost a lot of money to be able to drill a well. So you kind of want to know where you're going before you start drilling. And the way you do that is a little technique called seismic reflection. Okay, seismic reflection is something that's been around a long time, about 6 decades, but we actually use something like that now that you've seen. And so if a woman is going to have a baby and she wants to go to the doctor and to make sure the baby is safe and healthy and everything else, they perform on it what is called an ultrasound. Okay, and everybody's probably heard of that, produces sonogram. And how that works is you put a device on the woman's stomach and it shoots out high-frequency sound waves that penetrate through the skin, penetrate everything, hit the surface of the baby, and bounce back up towards that device, which also has a receiver on it. Once the receiver gets the waves coming back off that have bounced off, it can then image what the baby looks like. Okay, and that's the way the ultrasound works. Ultra-high sound waves bouncing off of the baby coming back up to the surface. Well, they've been able to see what's underground doing that for many years now. 6 decades they've been doing that in the oil business. It is basically generating a wave by some method. The wave hits an interface between 2 different rock types, bounces back up to the surface. And you can image way down 10, 15 miles deep to see what the shape of the strata are underground. Okay, and so that is how then we can kind of see what things look like underground before we drill a well to them. So maybe we can see what we might want to drill at rather than just drilling blindly. Okay, now we have a little device here that I put together so people can see what seismic deflection looks like. And what you can see here is a box, and it is made out of plexiglass shelves. Okay, so you can see all these, you see it's plexiglass on the top, but I'll tell you now that there's a bunch of shelves underneath there. And I could say to you, how many shelves are there? And you can say, you could take a guess, or maybe if you look on the side, you can see. But otherwise, how are we going to tell otherwise without pulling this apart to see how many shelves are, which is a pain in the neck, pull it apart to put it back together again. What we can do is we can take a little laser pointer and we can just turn that on, and you will see that all the dots come up on the back, and you can count them, and you can see there's 4 dots, which means there are 4 shelves. Then what's happening is that the laser is hitting each one of those shelves, reflecting off of there, and the little dot is coming up to the surface. Okay, so with that, without even pulling it apart, I know how many shelves are there. Now, if I'm careful to slide it across, I can even see what shape those shelves are. So you can see that the top 3 are pretty much flat. But look at what that bottom one is doing. That's tilted. So with this, I can see the shape of the shelves, and I can see how many there are. So this is giving me some idea of what's underground without having to actually dig a hole to it. So here are 3 things that we have put together then to help define our different types of oil accumulations. We're going to use all 3 of them now. We're going to put them together, and we're going to find out what are called oil and gas traps.
Stop, pause there, please. Because we like to be fair, they can infer, please note, they can infer the age of sedimentary layers by doing tests on those sills that you see on that diagram. They can actually date those sills and infer the sedimentary layers between those sills and give them an age. You can also date carbon-rich layers, but usually up to 50 to 90,000 years. But however, please note, because they're in sedimentary layers, I'm going to quote you from the Natural Radioactivity in Geologic Environment from the National Nuclear Security Commission, okay? They state, radioactive elements in soils, secondary deposits formed due to the leaching of uranium through minerals during chemical weathering. Uranium is mobile in groundwater, but it is readily precipitated by humic acids in soils. It may be found in carbonized plant or animal materials and may also fill openings in porous soils. So even if they did infer an age, it would be contaminated. You can't reliably and accurately date sedimentary rocks. It's impossible unless they infer and make heaps of assumptions about it. And as you'll see that in all the discussions that I've had and the videos that I've watched, not once did they mention the dating of rocks as a criteria to actually find the oil wells. Okay, well, if you'd like to add anything more there.
I was just going to quickly point out that there's been so many good comments in the chat. Our superstar audience is helping make this video that much better with their comments, in addition to the debunking that's taking place in this video. Jamie says that ends it, unless they want to throw out uniformitarian principles, which was what shifted the biblical model in the first place to deep time. And then I can hand it over to Steph if he'd want some comments. Doki Doki Bible Club, $5 super sticker. Thank you so much, Doki Doki. You guys are awesome. We appreciate it. Doki says, today everyone admits dry falls happen quickly from flooding. Did you learn in school days, Steph, dry falls took millions of years to form?
Sorry, the dry falls. Can anyone tell me what is meant here?
I'm not too sure. Maybe Doki could, or George, brother George.
I've never heard that term either, so
I've
I'm
heard
at a
that
loss,
term.
to be
I've
honest.
heard that term in connection to ice age things. So I'm not sure because it has nothing to do with the subject on hand. So
Yeah, no.
Maybe he's talking about a place like Dry Falls in Highlands, Northern Carolina. Maybe he's talking about a place.
Yeah, that's what I'm thinking. But yeah, no problem. And thank you, Doki, for the Nicholas confirmed that. Dry Falls in North Carolina.
yeah,
Pause
I've
it
never
there.
been there.
Pause it there, Matt. Again, you'll note how easy it is to do seismic reflection studies. It's merely, as you can see, that guy tapping on the surface with a hammer, but I think it's a bit more involved than that. But you'll notice they do it through sedimentary rocks. They collect the information and do their studies. I'm sure the geophysicists know how to do it and how they interpret that information, and they then target in on a particular spot to make the drilling more efficient, if you like. Again, to be fair to Erica, again, yes, you can infer a date of a sedimentary layer, but it's not reliable and it's not accurate because of contamination through leaching. Okay.
I can add something about this. This seismic seismic investigation reflection is very complicated. It's very complicated to come to conclusions and to the correct conclusions because you don't have a velocity model. You will need to establish a velocity model first. You need to know the sound of the speed of sound in the earth. And that varies with the porosity and with the density of the rock wherein the sound
Yes.
is moving.
Yes, correct. Different materials have different, I guess, frequencies or wave distribution. So they can actually determine what kind of material it is.
It is very complicated, and therefore
yeah.
they use exploration drills to get a better insight in the velocity of the sound.
Yeah, in the next part of this video, they'll talk about the 4 main traps where they actually find the fossil fuels. Okay, and you'll see an illustration there with those 4 oil traps. And what they'll do in the next part of the video is actually go through each one of them and explain how they're likely formed. But keep in mind, again, I'll say with the anticline trap and the salt dome, notice the shape of the layers. We'll talk about those later. And in the other ones, notice the fault lines and what we spoke about, the pressure that this fossil fuel is under, and how you'd expect under hundreds of millions of years that oil and gas should have leaked via those faults in the sedimentary and shale layers. So, Matt, if you can play the next part of the video, I think it's around 6 minutes. But you'll see at the end. We'll stop and we'll go through each one of them, and we'll actually add some comments so people can actually ask questions as we go through each of those 4 particular traps. So bear with us. As I said, it's around 5 to 6 minutes long, but they describe each one in detail. Thank you.
So here are 3 things that we have put together then to help define our different types of oil accumulations. We're going to use all 3 of them now. We're going to put them together and we're going to find out what are called oil and gas traps. Okay, so we're going to use the density, porosity and permeability, and seismic reflection all together to define oil and gas traps. Okay. These are pictures of oil and gas traps, okay? And we'll start off with, and that's what an accumulation is called, a trap. Okay, and so what we'll start off with is what is called a stratigraphic trap. And this on this side is a stratigraphic trap. This is a block diagram. The green part is the surface of the Earth. Everything else is looking down into the Earth. Okay, so these are cuts down into the Earth. Now, if you look, you will see a wedge-shaped area on the first one, on this stratigraphic trap, and it is encased in brown. Okay, now the brown is caprock, and the wedge-shaped area is reservoir rock. So in order to tell what shape it is underground from the surface without having to dig down there, and digging would be very costly thing, we would use seismic reflection. So the seismic reflection will tell us that there is a wedge-shaped body underground. We know, so that's the first thing we're using. The next thing we're using is that we know that the brown is caprock and the wedge-shaped body is reservoir rock. So that's the second stuff that we talked about. Now, if you look inside of it, you'll notice that it's white on top, black in the middle, and gray on the bottom. White is gas, black is oil, and gray is water. So it's in the same order that we talked about for our density. So all three are applied to this feature. Okay, so that's the first one. Second one, we can over and look at this, which is called an anticline trap. Now, when two continents smash into each other, or a lot of other ways too, rocks can actually be folded. Okay, and they can fold down into a U shape, or they can fold up into an arch shape. And an arch-shaped fold is what is called an anticline trap. Okay, and so this is a picture of an anticline trap. You can see again, surface is green, and we can see underground the brown is the caprock. The one underneath the caprock is our reservoir rock, and once again, we can see gas, oil, water in the same order. So therefore, we can see that both of these are taking all three of our concepts and putting them together to make oil and gas traps. Okay, and if we look at both of these and kind of stand back and look at them, we will see that the oil and gas in both examples sits right at the top of the structure. So as I said, always drill high, always drill at the highest point, and you can see clearly that that's exactly where you need to go on any feature that's geological. Okay, we have a couple other types of traps here. Down on the bottom is what is called a fault trap. Okay, and a fault, not only does it produce earthquakes, but it can also offset layers. So you can have a continuous layer of reservoir rock that then is cut by the fault and then placed up against, shoved up against caprock. And that will encase it in caprock and allow you to accumulate gas on the top, oil in the middle, water on the bottom. And so that's another type. Last type is what is called a salt dome trap. Now, in some areas of the world where we have very high evaporation, hot temperatures, where a little sea might be cut off from the main ocean, you can get conditions of what are called hypersalinity. Huge amounts of salt accumulating in these things, and the salt can actually deposit on the floor of the ocean. So you get salt depositing, it can be quite thick on the floor of the ocean. Now, later on, once you add clay and sand on top of the salt then turns very squishy, and it kind of acts like toothpaste, and it's very light. And so you squish it down with that sand and clay, and it can squirt back up to the surface in what is called a salt diapier or a salt dome. Okay, and these salt diapiers or salt dome are where we get our table salt from, or even our road salt. They mine these. Okay, but the other thing they do is if you have layers of trap rock and cap rock on top of reservoir rock, they can bend everything up and you can get big accumulations of oil and gas around them. And if you get these big accumulations, these can be worth a lot of money. We get most of our oil and gas in the United States from the Gulf of Mexico. And in the Gulf of Mexico, the big plays are these salt domes. A single salt dome can have 2.5 to 3 billion barrels of oil. Last year, oil was selling for $100 a barrel. So that's $300 billion a single salt dome can be worth. That's more than most companies in the United States. Okay? More than a lot of countries. So that's how much things are worth if you can find the right trap and drill it. Okay. So that is the background material then for this oil game. Okay? And this is the oil game.
Okay, pause it there, please. As I said, the link to that video is provided, so you can watch it to the end if you want to. But the rest of the video really wasn't pertinent to what we're going to discuss. So what we'd like to do now is go through each one of those traps individually and talk about those. Okay, you'll notice that as you mentioned, the first was the stratigraphic trap. This was on the top left-hand corner. Again, you'll note the order and the densities of those materials, where he mentioned the gas, the oil, and the water reservoir rock. Okay. Now, how do you think, under uniformitarian assumption, you can get that wedge in that shape with a fault line, obviously going up to the surface, and that oil remaining there for hundreds of millions of years, possibly billions of years, and not actually escaping to the surface?
Yeah,
Steph, you might like to talk about the pressures involved.
Yeah, because keep in mind that oil and gas is found at a depth of, well, by example, 2,000 meters. And then some quick math learns us that there is a huge pressure in there. The pressure is 40,000 kilopascal, and that is equivalent, well, George mentioned that already, is equivalent to 4,000 kilograms per square meter. So do you honestly think that oil will exist under that pressure for hundreds of millions of years? It would have leaked out through fissures and faults you observe in the rock layers a long time ago. Yeah, so I don't see the point here of...
if you move to the next one, we'll talk a bit about what I mentioned about the shape of these cap layers. Just pause it there, Matt. Can you go back one, please, to that? To the next one.
Yeah, that's the anticline.
That
trap.
one there. Yeah, that one there. Now this is the anticline trap. Again, I'd like to reiterate. Notice the shape of that cap rock. Okay, the cap rock is a shale. It is hard. It is rock hard. To get that shape under a slow-moving Earth, you would expect, due to the bending, you would expect cracks. Now, I've done quite a bit of research on the bending of these rocks. You can bend the shale, but it needs to be done at approximately, I think, 210 degrees centigrade. There are some reports that you'll find in the description of two studies that were done, one in China and one in Japan, where they actually noted that the ductile capability of shale it can be observed at around about 4.5 to 7 kilometers. As I said, you'll find those in two papers, one in China and one in Japan. Now, considering what secular science or science in general says about the geothermal gradient of the Earth, that is the temperature of the subgrade as you go deeper into the Earth, they approximate that for every kilometer of depth, you should get an increase of 30 degrees centigrade. So, Matt, if you go to the next one, which shows the graph, the geothermal graph. Yeah, that one there. You'll notice the y-axis is the depth in kilometers. Okay, so in the first 410 kilometers is that approximation of 30 degrees centigrade for every kilometer of depth. If you go to the next one, the next description, the figure, In this one here, it talks about the ductile deformation of granite. Now, in the case of granite, you'd expect it to, as you can see there with the reference, the ductile deformation occurs between 10 to 20 kilometers. We'd like to point out that there is a difference between the ductility of granite to the ductility of the shale. That's why I mentioned those two studies that were done in Japan and in China, where they clearly show the ductile behavior of the shale is different to the granite. Okay, so we're not saying that you need to go down 10 to 20 kilometers to get that ductile behavior of the shale without it cracking. What we find is it occurs between, as I said, 4.5 kilometers to 7 kilometers, depending on the type of shale. Now, you'll also note that in these videos, they mentioned that the oil was found at 2 kilometers, okay? So where is the difference between the 4.5 kilometers to 7 kilometers of depth that's required for the ductility of that shale without it cracking, and the 2 kilometers that we find the oil? Somehow at least 2.5 kilometers of material would have had to erode for it to be found at 2 kilometers under the ground at present. Okay, so what's next?
Yeah, what you can say then, so where are these eroded layers now?
Yes. Yes, I mean, if you use their own literature on erosion rates, some of you in the chat might remember I've spoken to Olga and mentioned some of these reports that are freely available. You can search for it on the internet yourself. They claim that the erosion rates are at 60 centimeters per 1,000 years. If you apply that erosion rate to that 2.5 kilometers, you get something like 40 to 70 million years of erosion. If that did occur, before I go to the next point, that 60 centimeters per 1,000 years equates to the entire landscape of Earth being eroded to sea level within 10 to 12 million years. So in the case of these oils, if that strata lifted by 2.5 kilometers, that would take something like in the approximation of about 60 to 70 million years. That's impossible. That contradicts their own studies that they've done on erosion. So,
especially since in these we find these fossils that have lived there the last 60 millions of years. So if they say it's all been eroded, then how can you find the fossils?
Exactly, that's right. Why do we still keep finding the fossils? And by the way, this is a link to one of those reports I mentioned. This was in China. You'll notice that they found the ductile zone at 4,470 meters. Okay, that's roughly 4.5 kilometers of depth. You'll note in the next paper that was written, it was a study done in Japan of a shale as well. And Matt, if you can go to the next screenshot. In this one here, you'll notice that they say the ductility range occurs between 175 to 210 degrees centigrade. Now, keep in mind what I said previously about the geothermal gradient. If you apply that geothermal gradient to those temperatures, you get approximately 5.8 to 7 kilometers of depth for that 175 to 210 degrees centigrade range. So summarizing that, based on the study that was done in China and Japan, you would expect that the shale to deform at approximately 4.5 kilometers to 7 kilometers depth. Okay, so that's just reinforcing what I was saying about why isn't that cap rock broken up? And if the only way that I can go is if you assume the global flood, it's easily explained. The shale was moist. The movement of the continents via a moist layer caused it to bend without cracking. You'll note in this particular image here that fault line. Okay, that fault line obviously is an access point for the gas and the oil. You would think after hundreds of millions of years that gas and the oil and the pressure that it's under should have found its way to the surface, and we shouldn't find any gas or oil in that fault trap. Okay, so if you could go to the next one. So just hold on. The 2 points, as we mentioned earlier, Steph made the point where are these eroded layers? 2.5 kilometers at least, 2.5 kilometers of eroded layers. Where are they? Also, keep in mind, ask yourself, why do we still find fossils if they supposedly lived 60 to 70 million years ago? Because we find T-Rex and dinosaur fossils. That's well within that 2.5 kilometer range. If that erosion had occurred, we shouldn't be finding any of them. Okay, Steph, this is your specialty, so I'll let you talk about the salt dome traps. But
Yeah,
what I'll say is, notice they put a uniformitarian assumption into the way that that dome was formed. All I have to say to that is, those layers were rock hard. You cannot form that shape through those hard rock layers without it cracking. Notice the surface cap rock. It's there trapping the gas and the oil. If it happened while it was still hard, there would have been cracks induced, and you shouldn't find any of those fossil fuels. Okay, it's over to you, Steph.
Yeah, well, what we are looking at is evidence that this was all in liquid phase when this was formed. This is the salt is from a primary igneous origin, and it's domed up like in a lava lamp. And it found its way in the mud of the flood. So the mud gave way, it gave easily way. And another thing that he said that the sedimentary rock on top of the salt is more dense than the salt itself. Well, that's not true. That's in solid form. What we are looking at here is that this salt dome is more dense than the sediments on top of it. So if this salt dome is moving, then it's going back, it's going down. However, when it's in liquid form, in molten, when it's molten salt, then it's less dense and it is buoyant. It can come up into the mud of the flood. So it's all flood evidence what we are looking at. And
the other interesting point, Steph, is in your previous presentation where we talked about the salt domes. Just go back, please, Matt, for a second. No, to the one with the salt dome. And
then George, once you're done this part, brother, I'm going to take a few minutes to go over the super chat.
No worries. You'll note in the previous presentation that Steph and I gave on salt domes, we talked about magmatic material, which was hot. Okay. People talk about the heat problem. Well, there's a situation where you've got a hot magmatic salt dome providing the heat that's necessary to form the oil. You need around about, we'll explain this further later on, you need approximately 300 degrees centigrade for that oil to form. So I just wanted to make that particular point before we go to the next illustration.
Yeah, that's a good point indeed. That's yeah, because in uniformitarian IDs there is no heat available to make this oil, and the salt is providing the heat. Yeah.
Yes, and we need to reiterate that cap rock layer is bent, okay? And what that particular person mentioned in the video was the salt pushed itself up through the layers. Now, those layers would have been rock hard. Rock hard layers don't bend like that without cracking. So that's what I'd like to say. Just for your information, you would have heard that he mentioned just one of those salt domes can contain between 2.5 and 3 billion barrels of oil, right? I think at one stage the price of oil was $100 per barrel. That's $300 billion worth of oil deposit there, and that's serious money. You know, I mean, it's currently I think it's around about $40 per barrel, but you can see how much money is underground in some of these salt domes. And just my discussions that I had with the Associate Professor David McQueen yesterday, he estimates over 50% of the oil deposits are found near salt domes or near these salt traps. So you can see how much oil is actually near these salt domes and why they look for them. Yeah.
Awesome point, George. Oh no,
yeah,
I was going to go over some of these questions now before we lose them, and then we'll move on. Is that okay, Brother George?
Yeah, go for it. I was going to suggest that you continue with what you said earlier.
Yeah. From my perspective, so many good points. I mean, even if I pretended to be a uniformitarian evolutionist, I could not refute the information being presented in this video. So this is awesome. Steph and George, you guys are warriors. So I want to thank you for all this. I mean, this is awesome. We've got people in the chats pointing out the fact that they're going to have to rewatch this a couple times just to digest all of this amazing information. So we've got a lively chat. We've got over 40 people, guys. Smash that like button. Doki doki. Thank you so much for the super sticker. We got a super chat here from Damian Garcia for $20. Thank you so much, Damian. You guys are the superstars of this channel. You guys are the reason why we're able to put out so much content, host so many debates and interviews. So God bless you all. Damian says, I appreciate the wealth of information that has come out of this channel. Thanks for the hard work and dedication, Team SFT. Looking forward to learning a lot more. Amen. Thank you so much,
Damien. Thank you.
Thank you so much, Damien. God bless. There's a lot more to look forward to. We've got some really, really awesome interviews that we are really close to confirming. And please, Steph, you're getting a lot of compliments in the chat. So I want to point out to everybody in the chat, for more of Steph, go watch his Salt Dome discussion we had with him. Well, it's got to be a few weeks ago now. Time flies by. So definitely check that out. In my opinion, irrefutable. We've had no objections or anything that we've even had to deal with yet. So let's see what else here. We had another super chat here from Doki Doki. Doki Doki Bible Club. Thank you so much. $5 says, what evidence is good enough to impress a geophysics teacher and change his mind? Not naming names or, you know, a lot of this brings me back to 2 Peter 3 that talks about how in the last days there's going to be scoffers denying three things, right? The creation, the global flood, and the coming judgment. So it's fulfilled. It's fulfilled prophecy, what we have here, where all the evidence in geology. Yeah, go ahead, George. Go ahead.
I was just going to add with my discussions with a geophysicist that I had a week or so ago, and as well as David McQueen yesterday, that, you know, what you hear about secularists and the education system, they are afraid to come out. If they say anything that contradicts the uniformitarian view, they're out of a job. That's as easy as that. He mentioned the wealth of information that's contained in these drilling cores, and they have the information, yet they won't release it because it's so damning to the uniformitarian view. These geologists know about this information, but they're too scared to come out with it, because we know what happens to anyone who contradicts the worldview. That's as easy as that. So again, I'd like to iterate. What was that you said about dating rocks and oil exploration, Erica? It plays no part in it. I've got a couple of quotes here I'd like to mention. These are stalwarts, okay? These are stalwarts, not only of creation, but also of geology, particularly John Whitcomb and Henry Morrison. Henry Morris, my apologies. I won't repeat the entire quote, but I'll go ... Such techniques as have actually been found helpful in exploration do not really depend upon the historical aspect of geology at all, but only on recognition of the structural and sedimentary markers that experience has shown are associated with such deposits. We just spent the last hour or so explaining those sedimentary markers. Furthermore, they go on to say it's mostly about rock strata, type of rock distribution, and geometry. It has nothing to do with the dating of rocks, Erica. Thank you. We're nearing the end.
You did great, George.
Yeah.
They're so desperate for evolution to be valid and important that they basically make these ridiculous claims like that one. You know, they're like, oh, well, without evolution, you guys couldn't even find oil. That's how important evolution is. In reality, we know the truth. They're just winging it. It's so embarrassing.
Yeah.
They say the same.
Yeah, Matt. Yeah, Matt. I think you've got some really good stuff to show after this in a couple of short videos. One which I compiled, and there's also another one from a secular educational stream about how long they expect oil to last.
Oh,
so
wow.
How much oil is left on Earth? Yeah. So if you continue the rest of that, this is it here. Yeah.
All right, here we go.
We spoke about most of these in the last hour or so. Continue on. Yeah, we introduced you to that last map in the previous discussion we had with Steph on the location of those, and that one there, and that next picture of the money. We're talking serious money involved in oil exploration, as Erica mentioned in her introduction about the $250 billion that's invested. So there's a lot of money out there to be made out of oil, and I don't know whether they'll these climate change proponents are going to be successful in stopping that. But yeah, I think the next video, Matt, with what was it on how much oil is left on Earth? Sorry, yeah. I'm going too fast actually. This is what I wanted to mention about the research that was done by the CSIRO, which for those of you that aren't familiar, it's the Commonwealth Scientific and Industrial Research Organisation. It's an organisation set up by the Australian government, and they actually have done experiments, a number of experiments, to determine how oil is actually made, and you'll notice they tried in weeks 50, 100, 150, 200, and 250, and 300 weeks. They had containers, and they varied them in different temperatures of 150 degrees centigrade, 200, 250, 300, and 350, and 400. They put them in stainless steel tubes, and they actually subjected them to these kind of temperatures. What they found was crude oil actually forms at roughly 300 to 350 degrees centigrade. Keep in mind what we said about those ductility ranges of the caprock layers. They occurred at 210 to, I think, 175 to 210 degrees centigrade. So somewhere that heat must have come from somewhere. And as we said, people complain about the heat problem, during the flood and the salt domes. Well, there's your heat that was required to actually form that crude oil. So if you can go to the next one, I can't remember what we were going to talk about next, but these are some articles that I found of how oil is formed and where you're likely to find it. So you can read these articles yourself at your own leisure. The links, I believe, are provided in the description. So by all means, do all the reading you like. I spent probably 3 weeks, closer to 4 weeks, doing this research. So you're welcome to any of it. You may object to the fact that it's a creation.com article, but please note they reference secular investigations and experiments. Okay, that's not as if, yeah.
Well, remember right here. This is how typically Team Dodgeball and the evolutionists. This is typically how they read creationist literature. They say they want to be up to date and represent us without invoking a straw man argument, but typically they read our papers and our work blindfolded. So that's probably why they keep misrepresenting and straw manning our position. So I just wanted to point that out. George, keep going, brother. This is really good.
October 22nd, 2015 marks World Energy Day, when we observe the need to take environmental action in the face of energy dependence. This holiday originated at the 2012 World Energy Forum, intended to address the future of oil and sustainability. Although peak oil usage was supposed to have occurred in the 1970s, today production and use is as high as ever. So we wanted to know, just how much oil do we actually have left? Well, unlike more modern forms of energy, crude oil is a non-renewable resource, meaning that once we use it all up, it's gone. Almost all of the world's oil is located in vast reservoirs, centralized in a number of countries. However, whether that oil can actually be extracted is referred to as proven or unproven. Proven reserves simply means that there is a 90% chance of the oil being extracted, and we know it's there. Unproven generally means that we believe it's there, but for a number of reasons can't extract it with certainty. Generally, oil estimates focus on proven reserves. So how much oil is still left? Well, as of 2014, the Organization of Petroleum Exporting Countries reports that roughly 1.5 trillion barrels of proven reserves are still available. For comparison, some have estimated that 1 trillion barrels have been used since commercial oil drilling began in 1870, although other estimates vary wildly. And while a century and a half seems like a pretty long time, oil use has been rapidly increasing. Today, the world consumes about 34 billion barrels a year, with China expected to account for half that usage within the next 5 years. But China only holds about 32 billion barrels itself. Roughly 80% of the world's oil comes from the 12 members of OPEC, with roughly 2/3 of the oil located in the Middle East. However, the single largest reserve on the earth is nowhere near most of the other OPEC countries. 20% of the world's oil is located in Venezuela, South America. They reportedly hold almost 300 billion barrels. Saudi Arabia comes in close with about 265 billion barrels. The third highest reserves, though, are found in Canada, which is a non-OPEC nation. In fact, of the 285 billion barrels held outside of OPEC countries, more than 60% is in Canada. But how long all that oil will last us is a somewhat shaky subject. Some say that we'll soon end up relying on unconventional oil extraction like fracking to power the world. Others say we'll make a shift to alternative energies like solar or wind before it's too late. But the most recent estimates by British Petroleum say that we have a little over 50 years before the oil runs out. Still, almost every figure, including the amount of oil reserves, consumption rate, and number of years left, has been widely disputed, and past estimates are repeatedly revised. So, how much oil do we really have left? It seems like nobody really knows.
Yeah, if you can just stop it there, please. Notice what he said. They continuously revise these figures. No one's got a clear idea of how much oil is left or how long it's going to last. Okay, but in summary, what I'd like to say, I mean, the next few screenshots of reports, again, that you can read for yourself, and those descriptions are those links are provided in the description. But what I'd like to say in summary, right? Oil exploration consists primarily of the search for a particular underground geometry where oil might be trapped in the rocks. And please note, oil is where you find it, as they say, right? The age of the rocks or the source of the oil is not of importance. Without doubt, beds can be correlated by studying microfossils. But this has nothing to do with the age or evolutionary ideas. Certain spatial patterns have been noted in the last hour or so, but they fit just as well, if not better, in a catastrophic flood framework as they do in a uniformitarian evolutionary concept. And I'll go as far as saying the catastrophic flood explains everything that secular scientists propose as the origin for the oil. So don't be fooled in what these people tell you about, that they need to date the rocks to find the oil. It has nothing to do with it. Erica, you cannot reliably or accurately date sedimentary rocks. You've got to sack your advisor. He's telling you baloney. So thank you.
Well, here's what results, and we've seen this in the 11 or so videos so far that we've done debunking her material on genetics, her Dr. Joshua Swamidass interview, for example, her attacks on Dr. Jensen. This is what results when you just parrot or repeat arguments from other critics, who in turn, they've repeated it from somebody, right? These arguments haven't been fact-checked. They've been debunked over and over again. This is one of the most detailed debunking of their claims on oil exploration that I've personally seen. So I just wanted to point that out, Brother George, that's exactly what results when they're just repeating arguments.
Yeah, I'm sure, SFT, that she gets her information from, you know who I'm talking about, Mr. Literature. we all know who that is.
Right.
So
yeah. And then who does he get it from, right? So it's just this ripple effect. So yeah, this has been.
Oh no, I know who he gets it from. He gets it from Berkeley.
Right. So I know we're not done yet, but I'm going to put the challenge out there for them to even attempt to respond to just one of our videos refuting their position. This one being probably way too difficult for them, but yeah, keep going. This is great. I just wanted to point out that the audience is enjoying it. Very lively chat, and time is flown by, George. So
yeah, the next few screenshots are really of documents and articles that I found on the internet that people can read at their own leisure. There's no point in me going through each and every one of those. But Matt, if you can just just pause it there. Please read that. Shh! Don't tell those evolutionists that dating of rock layers has nothing to do with oil exploration. In fact, you can't date sedimentary rocks reliably or accurately. This exposes another lie they've been told and swallowed. I'm amazed how much swallowing these evolutionists do. We can only wonder what other lies they've swallowed. Unbelievable. Please wake up. How many times have I actually said to these evolutionists, wake up, slap yourself in the face and wake up.
It's nice to see that many of them are waking up, but a lot of the members from Team Dodgeball, not so much. Steph has personally seen it. So with Steph's amazing work on salt domes, there were some criticisms however many years ago. And Steph dealt with them on creation.com. He's got an article where he systematically refutes each objection and criticism coming at his model. So Steph, I want to give you credit for that. That was really good.
Yeah, thank you.
The other thing too, SFT, we should note that you could consider this part 3 of the series we mentioned with the first lecture that Steph gave. The second one was on the salt domes. This would be considered part 3, and part 4, which Steph is working on at the moment, will bring the marsupials and the KPG boundary.
Yes.
He's written a paper, and he will present the findings of his paper in another part that we will be doing in the next few weeks, hopefully. So
Yeah,
maybe Steph can add a bit on when we can expect to see that, Steph.
Yeah, well, it's. I see that Standing has a very tight schedule for many things what are coming on. So I don't know when I can present this.
Take your time.
Take your time. But whenever you're ready, Steph, we are happy to fit you in because people love you on this channel. We love you, and your information that you've been presenting is phenomenal. So.
Yeah. Okay. Well, I'm working on it, so you will hear from me. Yeah. Today I was occupied with someone had invited me to a drilling excursion here nearby, so that was
awesome.
fun. Yeah.
Yeah. I'd like to finish off with. I mean, Erica puts this in her videos where she's done with creationists. I think we're done with evolutionists. But I'd just like to add, I have tried to be as impartial as possible. I've presented both secular as well as creationist material, so that you be the judge of what we've presented. Okay, you do your own research and tell us whether we're wrong.
Right. Yeah, I want to point out the fact that, like, for example, Dodgeball Dan, right? So he's not confident enough to say this, and Erica would not be confident enough to say this either. But I say to the audience, both atheists, theists alike, go watch their videos, then watch our video responses. And people like Gutsick Gibbon can say all day that, you know, she's not being addressed appropriately. But here's the thing. When you look at both sides, I guarantee you're going to come, as long as you're being objective, you're going to see who's actually presenting the data, presenting it honestly, not dodging the arguments. So that's my challenge to both sides of the argument. Go watch both sides. Somebody in the chat said, you know, why do we care about Conrad here? So he typically jumps in last minute, never really has any actual rebuttals to provide. He says, why do we care about Erica's opinion? Two things. We don't very much care about her opinion, but she put out a 3.5-hour video, so we are dealing with it. But here's the thing. Erica has actually parroted this from other people, right? RJ Downard, I've seen articles from uniformitarians on this issue. So by dealing with Erica and her video on this specific argument on oil exploration, we're actually just dealing with now a very commonly used argument against flood geology. So I wanted to point that out. George, go ahead.
SFT, I'd like to say if you're not worried about misinformation, then there's something wrong with you. You should be correcting misinformation. Otherwise, you get indoctrinated by all the BS that you're told. But before we close up, I'd like to thank Matt. I think he stayed up till about 2 o'clock in the morning last night preparing this stuff, and also to Steph for his suggestions, his recommendations in the in all the research that I've done. I've had to go to Steph a few times to get some opinions. I'd like to thank David McQueen, Scott Devlin, both experienced in geology and geophysics, and to you too, SFT, for giving us this opportunity to actually present some of this information for everyone to digest.
Absolutely.
Well, thanks, George, but you did a terrific job here.
Thank you.
Yeah, it's amazing what you gathered.
And I'm starving because I haven't had breakfast yet. You guys are in different parts of the world.
Yeah. Yeah.
Well, yeah, that was awesome. It's been almost 2 hours. We've still got 40 people in the chat, so looks like a last minute super sticker from Doki Doki. Thank you so much. I hope you guys enjoyed. Of course, as always, any questions, anything like that, please let us know. We'll do our best to answer them, especially if they're honest questions. Actually, one super chat we didn't get to. It was just a brief, it was a question out of curiosity from, I did save it in my images. So let me go find it real quick from brother Jamie Russell. Let's go see here. Oh, here we go. Jamie Russell, $5 super chat. Thank you so much. Thank you for your patience, Jamie. He's just wondering, are the speakers familiar with a Dr. Ariel Roth from Loma Linda University? I'm not personally familiar with who that is, but
yes, I am. I've read a book from him. Yeah, he's well, he has published very good stuff. Yeah.
That sounds a lot like Aaron Ra.
Yeah.
Yeah.
Well, that's a bit different. This is Ariel Roth. I think so.
Yeah. Yeah. Anyway, so yeah, this has been fun, guys. If Steph, Matt, George, if you guys had any final words, I want to say great job to all of you. Matt, great job editing together that video. It's been a lot of fun, guys. And we got lots more to look forward to in the next week or two that we've scheduled. And I know everybody is already looking forward to having Steph back on. So we are going to work with Steph behind the scenes to get him on as soon as we can. For another.
Just one final comment. Expect to see another video disputing Erica's assertion about the constant radioactive decays. I think Matt is working on a refutation to that.
Yep. Yes, and I want to point out to the audience too. You'll notice we've done a lot of genetics videos recently, debunking her video. So now we're starting on the geology age of the earth section. So this was, I hope everybody enjoyed. And like George, like you said, we got a few more to come. So I think we're just about ready to shut it down.
Yeah. Okay.
Yep, thank you very much.
Thank you. One thing about this dry falls question,
yeah.
I will address that in my next when I'm on next time in a couple of weeks. I will address the dry falls because it has everything to do with flood geology and ice age, and I will address that when I talk about these marsupials and all that kind of stuff.
Awesome.
Yeah.
We're excited. I know I'm excited. So George, Matt, any final words before we shut it down?
Yeah, keep your eyes open. We're going to have the none other than John McKay.
Yes.
In the next few weeks. So he's another stalwart. He's a geologist, as you know. He's a creationist, a young Earth creationist, and I'm sure he'll have a lot to say.
Amen. Amen. We've got Dr. John McKay, geologist, scheduled for 2 weeks from now, guys. So I'm glad you brought that up, George. That's going to be, mark your calendars. I'll set the event soon so you guys can mark your calendars. And yeah, Matt, any final words, brother?
No, that was awesome. That was perfect. Good job.
Awesome.
Thanks, Matt.
All right, guys. Well,
thanks, Steph.
Yeah, thank you.
That was a lot of fun. I'll be rewatching it. I know a lot of people in the chat will too. Guys, thanks for keeping it fun in the chat, keeping it lively. Thank you for the super chat, super stickers, and God bless everybody. SFT is out.
For all those who appreciate the work that we're doing here on Standing for Truth, please hit that subscribe button because we are just getting started.